Hey, what's going on? Adam the Tutor here, coming at you with another Fourier Series video. This time we're doing one that's a little bit different. You know, not too different from the last one, but it definitely is a little bit different. And basically what we're going to be doing is we are going to find the Fourier transform of this f of x on the interval from L over 2, or from minus L over 2 to L over 2, right? Now, the first thing to kind of notice is that, well, where would I put my L over 2, or, minus L over 2, right? Well, we could say that, L over 2 is greater than 1 over 4b, in which case that would put our bounds somewhere out here, right? But basically then we'd be left with this region where our integrals will basically be 0, right? And that's not a very interesting case, right? So what we're actually going to do, right, is we're not going to do that. And instead, we are going to make this be an equality, right? So instead of L over 2 is greater than, we're going to make this an equality, right? And now we're going to see what happens. So basically, this is our limit right here, right? This is L over 2, and this is minus L over 2, right? When, so basically L over 2 is equal to 1 over 4b, right? Which is exactly what I said here, right? So our A is going to be 1 over 4b, right? So, with that in mind, let's go ahead and just kind of, let's go through these integrals, right? So, our first case is our alpha sub 0, right? Which would be, well, we'd have 1 over a, which would be 4b, and then we'd have times the integral, c from minus 1 over 4b to 1 over 4b, and then we have times f of x. Well, on this interval, right, this interval right here, which corresponds to this interval right here, our function is 2b, right? So we have 2b, and cosine of 0 is 1, right, because m is 0 right here. So what we'll have then is we'll have, let's see, so times 1 dx, right? And this is a pretty easy integral to evaluate. We'll have an 8b squared times x evaluated at these bounds. Well, that's just going to be 1 over 4b minus a negative 1 over 4b. And so that would basically be 2, or I'm sorry, not 2. I could write 2 over 4b, but we might as well simplify it. So we'd have 8b squared times, I did it again. I wrote 2 right there when I meant to write 2 on the bottom. Again, I could write 2 over 4b, but that's just 1 over 2b, right? 1 over 2b. And so that, right, I'm going to get a factor of b that cancels out here, and this 8 is going to cancel out with this 2 and become a 4. So I have a 4b, right? And so then that's our value for a naught, but then when we divide it by 2, we get that f of x is equal to 2b. So that's kind of interesting, right? We found a Fourier series for this constant function, and it wasn't even a series, right? It was just this constant. So we got back our original answer, right? So that was a pretty easy Fourier transform to do. And I thought it might be nice to do an easy one. And basically what I mean when we get this is because these other two integrals for alpha sub m and beta sub m, so maybe I was a little bit premature in saying this, but this will be the case. because basically these two are going to be 0. And now, why is that? Well, think about it. Here, you basically have some constant c times the integral from minus a to a of cosine k sub mx dx, which we know that that's 0, right? Because then we'll have 1 over k minus 1 over k sine of k sub mx. When you plug in the bounds, it'll be 0. And here for beta sub m, you basically have the same thing, except this is a sine, right? And basically, over a symmetric interval, the area under this curve will be exactly 0, right? You'll have a positive area, you'll have a negative area, and they'll cancel out. And it's the same story with this one, right? So basically, this is our answer right here. So, short little Fourier Series video. Kind of an interesting one, I think. But yeah, that's basically it. And yeah, so if you have any questions or anything like that, something I didn't explain all the way for you, just leave it in the comments section and I'll be more than happy to address it. And that's going to do it for this video. As always, thanks for watching, and I will see you in the next video.